Hi again, everybody. Thank you very much for joining today. I would like to welcome you to this new webinar from Scilife about sterilization. For those of you who don't know me yet, my name is Angel Badia. I'm the knowledge manager at Scilife, and with me we have Ronald Slob. He's the senior validation and qualification expert at QBD. And I would like to have Ronald introduce himself. So, hi, Ronald. Thank you very much for joining. Good morning.
Good morning.
And please introduce yourself.
Okay, I will be short and sweet. My name is Ronald Slob. I'm Dutch from origin. I'm working now for about 3 years for QBD, but when I started in 1990, I started as a validation engineer, mostly on sterilization processes, qualification, validation. And so at that time, I had a lot of experience of actually on the field jobs of how to be sterilizing and how to be qualifying and validating. And during the whole time that I'm still doing my job, I still got a lot of interaction with different kind of sterilization methods. So hopefully I can give you some information about what is on the field and how it works and where you can use it. So hopefully welcome to the world of sterilization.
Yeah, thank you very much. For sure, it's going to be very interesting. I hope it's going to be interesting also for our audience. So let's just review the structure of this training of today. So first part is this introduction by Ronald. The second part is the main training that will cover about 45 minutes. It is about the sterilization. So you'll see that all the sterilization processes that are carried out in healthcare facilities, you know that they are used to destroy or to eliminate any kind of microbial life that could also contaminate our products. And you know there are different sterilizing systems that Ronald will explain with detail during the training. There are several methods that can be used for sterilization, such as the steam under pressure sterilization or the dry heat sterilization. There's also the ethylene oxide gas and the vaporized hydrogen peroxide. So all of them will be covered today. And also Ronald is going to cover an introduction of the sterilization concept, and as commented, the overview of the sterilization methods and a detailed explanation of each one, right? So I just want to explain you that there will be some spare time at the end for the Q&A session. And here you will have time to ask anything you want to know from Ronald's presentation, to go more in depth in any particular issue. So meanwhile, feel free to send us your questions. You know, you can use the Q&A button below your screen. If possible, do not use the chat button. If you have specific questions for the session afterwards, use the Q&A button if possible. And for the people that have just dropped in, you know that the Zoom bar is below your screen. Right. So in any case, if you have any problem, you can give your comments by using the chat button as well. Right. So don't worry about if we do not have time for answering all the questions, because all of them will be answered by Ronald afterwards, after the session, and we will prepare a PDF page and we'll resend to you afterwards. So with all that said, and with any further delay now, right? So I would like Ronald to start with his training. So Ronald, go ahead. And now you know that the stage is yours.
Thank you. So the introduction we just had. So just want to start first to say about the terminology of sterilization. So yeah, what is really the sterile preparation? Now, sterile preparation is a sort of process that you ensure that there's no biochemical or microbial contamination of anything involved in the healthcare practices. Because there's a difficulty to show something which is actually sterile, because if you want to have a test method, you want to have something sterile to test something in sterile. So it's a sort of chicken egg kind of question. So the thing that they agreed on is, okay, what is sterile? So there should be a probability that less of 1 of a million is contaminated. So it doesn't mean complete an elimination of all the bioburdens, but it gives you a chance of 1 in a million. So there's always a very small chance that something is still contaminated. But just want to be sure that the terminology for everybody is clear, that it's 1 of a million is the possibility that it still can replicate. I think that most of the people here on the site itself or on the course itself, the training, will be familiar with the volume 4 annexes from the GMP. If not, I just took a small part out of it, which says a little bit about the sterilization. There's a lot more information in there, but the main part is where it's possible. If you want to sterilize, you want to sterilize it with heat, which is thermal sterilization. Most of the things that are common within the practices within the pharmaceutical industry and also in other industries is the use of steam. Steam is the most common way of sterilizing stuff, and it always will be preferred. If you can do a sterilization by steam, then you will use it. If you can't use it, then there are other possibilities or other options for trying to sterilize your product or your device or whatever. But the main part is that you first have to look if it's possible to sterilize it with steam. Because I'm also saying now that there are different kind of ways of sterilizing processes. I will go through that. I'm starting first with the steam sterilization, and I will go gradually to the other alternatives that there are for hand. Zip. Over here, you see this kind of overview of the sterilization methods, which are now commonly used within the practices. And I divide it into two different kind of stages. One is really physical, and the other one is chemical. And if you're going from left to right, you see that the first thing you want to do is heat. Heat is the most. I always try to say, okay, if you got something like boiling an egg, before that, the egg is still capable of producing if he wants to. But if you have a boiled egg, then it's no way that you can reverse that into a further life kind of egg part of it. So the first thing you come to do with heat is the first indication is you want to do it with steam. If you got other kind of things, the other way of doing is with dry heat, and dry heat is then some processes which going very high temperatures up to 250 or 170 degrees. The second part that you want to do is maybe irradiate the materials, and then is something like an X-ray, gamma radiation, or UV. UV is not really a sterilization, more decontamination, but X-ray is widely used within the pharmaceutical industry as a way to sterilize certain kinds of products. I will go in that later. And third, I have filtration, and filtration is just working on size exclusion. So you have a material, you have a bioburden in there, and you just want to remove the bioburden from your product. And it's just the way of biofiltration. You make the hole that small that your product goes through, and the bioburden or decontamination stays behind within the filter. those things, you also have then the chemical, which is then also widely used, but a different kind of mechanism behind it. It is working on a very active kind of vapor like ETO, vaporous hydrogen, or NOx, which then attacks the cells, the DNA structure when they are exposed, which also then reduce your bioburden to a certain kind of stage that you can say, okay, I still got a 1 of a million possibility that evidence that something is still there capable of reproducing. If you look then also with a small deviation on the backside is that, okay, if you go into heat, and then your product also must be heat tolerance. So yeah, you want to sterilize it, but you don't want to waste your product itself. So then you got the heat pump, and the other ones are non-heat tolerance, because you stay within temperatures with your product that you don't have any degradation of your product. So first, the most commonly used is steam. Steam is an exposure of saturated steam between, say, 1 to 121 degrees or 134. It depends on your policy of your company, which kind of temperature you want to use, but both are commonly used. But the most important thing is that it is saturated steam. You need saturated steam because the steam itself doesn't kill, but the transition from steam back into a fluid gives a lot of energy off, and that kind of energy you're using to kill your bioburden, and that you're doing by denaturation of your proteins. Just like what I said, if you have an egg and you boil it, you get a different structure of your proteins. That's the same kind of thing what you are doing with your steam. You give them a lot of energy off that you have a sort of boiled egg kind of thingies. So actually, almost it's mostly used for medical supplies, for media, for equipment. The fun fact is that it's really not 121 degrees, but actually it's 121.1, because the Americans were beat us to it, which is originally about 250 grade Fahrenheit. But most of the times, the 0.1 is discarded. So it's a high efficient process. Yeah, you can also see in the annexes and in all the guidelines that it is the preferred method of sterilization. And the most biggest advantage is it can penetrate inside your medical supply or in your vessel or in some other things, which most of the other sterilization methods don't have that ability. The most of the other sterilizations are more of, let's say, surface and an area contact touches, which then sterilize those kind of things. But really penetrating into a certain kind of device, steam is the only way you can actually do that. So it's very efficient, but it also relies on a lot of factors. For example, for sterilizers, you see the application sterilizers, steam in place, holding tank, freeze dryers, it's being widely used. But most of the thing is that you want to establishing the saturated steam. So it means that you must get rid of your air inside the chamber itself or inside the product, just to allow steam to penetrate inside your product that you want to sterilize. And that can have some challenges on the loads, on all kinds of things, and keeping your temperature under control with pressure. So it's a very efficient kind of way of sterilizing, but a lot of factors you have to take care of. The second one with on the heat is dry heat method, which is then most of the time the 170, 180 degrees. And you also have dipyrogenation, which is then about around 245 to 350. You also have these kind of funnels, which are going very high in temperature. And then it's not really that you are changing your protein, you're really burning your cell away. And yeah, it's no longer feasible to reproduce anymore, of course. And the higher ones, say that the deeper urination, is because when you are destroying the cell itself, on the cell, there are some lipids, some fat uses, which are still there, which are not killed, but still can cause a fever. So in the old days, people thought they got it. Yeah, we can sterilize, and it's not a problem. But still, they were injecting these things into the person. So and they still got fever, and some of the people actually died about that one. And it seems like that there was a small lipidus in the cell wall of the cell itself, which was still there. The only way you can get rid of it is just actually, yeah, raise the temperature to the 345 or the 300 or even higher, just also to burn those lipidus. It's got not so many limitations because it is just like a big oven as you have at home. Just be sure that your temperature is high enough and reach every spot that you want to have it. But yeah, you need longer times, you need higher temperatures just to get the effect that you want to have with steam. So it's 10 times less efficient as steam itself. Without the heat, we also have gamma irradiation. So that's just exposure to a gamma source. So that can be cobalt or cesium sources. And it also does the same thing. It's destroying the nucleic acids and distributing their DNA of your bioburden, which is in there. So mainly it's used for sterilizing consumables. So, yeah, everybody doesn't have a nuclear reactor on site. I hope not. So this is more of a contract supply that you're going to do. You have your stuff. You would say, okay, I want to have a gamma sterilization done with it, and you bring it to the certain kinds of a nuclear facility, which gives us a certain kind of dose on your product. The main advantage is that there's no heat in there. After the irradiation, there is no rest irradiation anymore. So it's not that it's coming out as a sort of glowing nuclear kind of thingy. It's quite fast, but the only thing is that the studies have shown also that when you get a high exposure of certain kinds of plastics, you also have the possibility that it's degenerating quite quicker than normal. So you want to give a dose for the gamma irradiation, but you just want to give it just enough, not an overexposure. Because if the overexposure, then it will actually degenerate your product. UV, same as sort of iteration, only yeah, just on a energy level much lower. Doing the same thing, destroying your nucleic acids. But really, yeah, I put it into there because it's commonly used, but don't think that it actually is sterilizing. UV is more or less used for decontamination or disinfection of certain kinds of things. Most of the time of surfaces, and then most of the time the start is your surface is actually also quite clean. You just want to give a sort of extra shot just to be sure that everything is destroyed by the UV itself. It is fast, it's easy, it's not so complex, it's not so expensive. And it can be used as a sort of precursor for disinfection parts, and then for actually for sterilizing. But I just wanted to mention it because you see it a lot of things in the industries. Completely different, but also as part of sterilization, is filtration. You have a filtration. Most of the time, it's a 0.22 micrometer filter, which is then doing an excise exclusion of the microorganism in your media that you're going through this. So that can be in media, but also can be gases. So air venting filters on vessels, which then also can have a sort of making the barrier between sterile and not sterile on one side or the other. The filter itself sure must be sterile, so that is also a thing. If you want to use it, that be sure that you have also a validated mechanism or a process to actually sterilize the filter up front. And there is the main advantage is that it's quite fast. That is the main advantage. And also on site, you can do a filter integrity after your process has been done. That there are different kind of things. You have a ball point test, pressure hold test. There are different kind of equipment, also suppliers who can supply you this kind of equipment for testing. But it gives you a lot of confidence because you sterilized over the filter, and afterwards you directly can check the filter if it was still okay. Yes, it was still okay. So I have a lot of confidence that the product which I have put over my filter is sterile. The one thing is this, because the product actually going over the filter, it can have negative advantages on your product itself. So there is also a lot of requirements wanted to look at the compatibility, extractable, leachables, so that you don't put anything additional in your product because it was going over the filter of a sort of kind of extraction. I've got another course, especially about filtration, because it's quite complex. If you want to use it, you can use it, but you need to have a lot of information if you want to use it. And it's a little bit too much now just to put it into one slide. Sorry. Then we have the gases, this VSP, also commonly used, but VSP is most of the time used for decontaminations of airlocks and for biosafety cabinets. Also, it's hydrogen peroxide, which is then very aggressive, attacks the bioburden, the microbiological cells, which also then is oxidation of nucleic acids and cellular proteins. So that's why this immobilizes the possibility of reproduction of your cell itself. Not really sterilizing, but more or less say decontamination, but it's a very good way just to get a clean environment or clean surfaces if you know that you're starting with a very low bioburden itself on your areas itself. And it's widely commonly used now. They got Steris, I believe, is one of the companies who can supply you this with kind of equipment just to show how you can do this and what you can do with it. And it's a very easy way. The main advantage for this is because afterwards you have your this hydrochloride, you have your water and oxygen, so you don't have any spare kind of residues after you perform this process. Just what I'm sorry was saying at the same time. In comparison with ETO, ETO is widely used. Also, same very aggressive kind of gas, alkyl, also DNA and RNA proteins. The only thing is that it's got a better penetration than VHP. It actually can go a little bit inside your product, but the problem is that it's highly flammable. You got a lot of toxic residues after your process. It's quite long. And also there are a lot of parameters which affect the efficiency of your cycle itself. Sorry, sorry, I was just babbling a little bit. Commonly used because just because it's one of the gases that has a little bit advantage that it can penetrate a little bit inside your product itself. It's got a very good rate of killing your microbiology, so really going into a sterilized kind of environment. But just what I said, the downside is that there are a lot of things behind it that can actually, if you don't want to use it, better to be avoided because you need very special equipment. You need a very high safety measurements around it, and so you see a lot of that you got these kind of vendors which can also do this part for you. And last is that one that I know about, but I've never seen it before. So I just give you the explanation that it's there. It's nitrogen dioxide. It's the same as VHP, for example. So the one thing that I heard is what I know is that it's using an ambient conditions, 21 degrees. So that's most of the materials then are not affected by any form of heat. There's also less sterilant residues, what you have with ETO. So I know that this is a sort of upcoming way of sterilizing, but unfortunately I don't have the experience at this moment. I've never seen it before. I know it. I know how it works. But you see this one is coming quite more into the field these days, and in also as a sort of sterilizer. So you can put something in there. So hopefully I went through all the possibilities that I know, let's say, for the way you can sterilize certain kind of things. So I want to go a little bit into depth to show you or to give you some examples a little bit about the qualification of validation of what kind of considerations. This is not all the considerations that I can give because every sterilization kind of method has its own back and downsides and advantages, and it's quite elaborate if I have to go into detail for everyone. So I just gave a sort of high level kind of assessment that I made for the different kind of sterilization topics. So you got your steam. Your steam sterilization is normally done by temperature mapping. 15 minutes, 120 degrees is the standard. It's an overkill situation. You got a strict relationship between your pressure and your temperature of your saturated steam. And that's the most important thing that you want to achieve within a steam sterilizer or in a vessel or when you're doing steam in place. You want to have direct relations. You don't want any air inside because air pockets or inside your system itself won't allow for the steam to condensate. And then what I've said in the beginning, if you don't have any condensation of your steam, then you're missing the major driving force of your energy in your steam sterilization. You can do that by temperature mapping and also by biological indicators, which is always a sort of combination that you want to do because the one is physically, the other one is microbiology. For the biological indicators, there say geostereothermophilus, which thermophilus also said something about where it's going to be used for. So these are very resistant, heat-resistant spores you use with a certain kind of amount, and you just put them with your steam cycle and you see afterwards if there still is a surviving rate, yes or no. They should be all killed. So if you have got consideration for your steams, and then it's the cycle development. You got different kind of processes you can run. Your steam quality is very important because your supply should be on a very high quality of steam just do his work or his job within the sterilizer itself. Loading patterns and materials. Loading patterns is that you must be sure that everything within your sterilizer or within your fermenter or other stuff is touchable or reachable for the steam. So don't pack everything together, because then you create a dead space. And also the materials, don't try to sterilize big things at the same time with small things. Try to be, if it's possible, of course, to group certain kinds of things you want to sterilize for in the sterilizer, because then you have a more or less uniform kind of way of working within the sterilizer itself. And the last point, which is sometimes overseen, is the dryness. Because you sterilize, say, for example, a scissor, and you put this one in these pouches. These are these Tyvek pouches. They are steam penetratable. But after you do your whole stuff, you have a nice sterilization, some kind of cycle. You know that everything is sterile, and then your pouches, when it comes out, it's still wet. When that pouch is wet, then you don't have the barrier of your pouch itself, from the material from the pouch itself. So you just contaminate your product again, and you put a lot of effort in there. So because you have a lot of condensation inside the sterilizer, be sure that also at the end you have got a nice phase to get everything dry again before you're actually opening the door again for your sterilizer after the cycle itself. The dry heat, it's at standard, is roughly, say, 30 minutes, 170 degrees. So yeah, and if you want to deperonate, you need longer times, you need higher temperatures. I also have a biological indicator that you can use. It's a Bacillus artiophaeus. Also, again, a spore which is very, very resistant for this kind of dry heat. You can put it during validation, but also you can put it into routine kind of processes. And then afterwards, look if there are still survivors, yes or no. So the considerations is also because you're working with an airflow pattern in a tunnel or within an oven itself, you also must be sure that the complete load can be touched by the heat. So there must be a flow behind it. So obstructions in these flows will have negative effect on your whole uniformity of your heat distribution inside a dry heat funnel or within an oven. Gamma radiation, minimum dose is 25 kilogauge. That's a sort of rule of thumb. There is some information about it. There are some guidelines for it, but this is more the guidelines because it's highly depending every time from what kind of material you actually radiate. But you can also use the biological indicators, which is this time a Bacillus spumilis, which is also then commercial available. So during qualification or validation of your irrigation, also maybe as in-process controls, you can use that indicator to look if there is still survivor after your exposure. Same for the considerations here is also the loading pattern. I've been once to a facility where they do this, and it's a sort of conveyor of things that they pass next to the source itself. Then also they rotate these kind of things. So the loading pattern of the things that you want to radiate, it must be very strict and must be tested before if it's possible that the whole thing has got the right doses at the right time. So the loading patterns and the uniformity, you can only have one material at the same time. If you want to do this, you can't mix the kind of things because the one is more dense than there is less dense, and it will influence, say, distribution of your radiation exposure. And also then also look for the maximum dose studies, what I just mentioned shortly in the time, that if you put too much dose, you think, yeah, more is less. So yeah, I'm okay with that. But if you got very high dosages, it also can negatively affect your product or your packaging material. So enough is enough. Don't go overboard. UV. We also use then the same biological indicator. Yeah, it's very straightforward, but just like I say, it's mostly decontamination of low bioburden surfaces. So surfaces that are maybe already cleaned with agents, cleaning agents, but you just want to be sure that you got a sort of extra doses or as a sort of storage. You see sometimes with the hairdressers that they also have these kind of scissors and that kind of thing they put into a UV booth just to be sure that there's no additional contamination anymore. It's also with loading patterns, you must be sure that everything is be touched by the UV radiation, because otherwise, if you stack something on top of each other, yeah, it makes logical sense that the other the part which is under the other one will not get the exposure from the UV. So the filtration. The most perfect thing is that you have a non-destructive retention testing of the filter, which you can do afterwards, which is, let's say, a bubble point of pressure hold testings. Then you challenge your filter itself in the test and to look if the uniformity and the gaps within the filter itself are correctly still okay. So, and also can do that with a biological challenge. Is een brief in muur, dat is 10 minuten. And the diminuta, it says a little bit of it's one that is very, very, very small, but that's going to be used more for if you want to do that in validation purposes to be sure that actually the media that you're actually going through the overhead filter still does not negatively affect the efficiency of the filter. So that's what the considerations is that, okay, the fit for use, your product and process conditions. Everybody's put something different over a filter that can be, say, from water to a high complex kind of media. They can all have a sort of different interaction with the filter material itself. The filter material itself is very inert, so yeah, the suppliers are not stupid, but it still have some influence on the characteristics of the filter itself. So most of the suppliers are very helpful with you to say, okay, what are you actually going to filtrate? Can you give us a sample? And they can do studies on site or off site with that kind of material, with the filter you want to use, to see that the efficiency of the filter that you want to request still is valid, yes or no. The sterilization method itself is also the biggie. If the filter housing, filters are normally assembled in filter housings. These filter housings have to also be sterile because you want to start from a sterile filter, because otherwise, yeah, you can non-sterile filter, it doesn't work. So also the sterilization method of the filter itself has to be qualified and validated, and normally it's also be done by steam, but also very complex because of the very small pore sizes of the filter itself. So must be sure that there's no adverse effect on your product. It also doesn't remove your active components. Sometimes it also happens with certain kind of substance that you got a nice kind of drug product, but it stays behind within the filter and you lost it. And one of the things is also extractables and leachables, where also the auditors and also the pharmaceutical industry are looking much more in it than they used to. So they also want to see that you show some studies, say for most of the times for end products, that you show that you have an extractable and leachable study, that nothing comes off the filters itself for a longer time or just during the process, which can negatively infect your product. Ethylene oxide, You got your biological indicators again. The Bacillus aerostabilis, which is very resistant against ETO. So that's your challenge bacteria. So the consideration is also your cycle development, because you need also to get rid of your air. You must have certain kind of pressures. You must have certain kind of temperatures. You must be sure that everything works optimized. Again, also the loading patterns. You must have accessibility for your product, because you put in a gas. A gas must be sure that it touches all the areas that you want to. Afterwards, because that's the downside from ETOs, you got residual studies. You must be sure that at the end of your cycle itself, that there are no residuals anymore within your product or in your component itself. So there's a lot of irrigations afterwards, a normal step of your but you have to show that there is in your process, or that you validated that there are no residuals anymore. Vaporous, also we have indicators in there, which is the stereothermophiles, the same one. Most of the time, it's very, it is the most easier way to qualify or validate, say, a certain kind of cycle, because you're actually challenging it with something which is microbiological. This is what you want to achieve with the reduction of your within your sterilization, with a reduction of your bioburden. So one of the biggest advantages is that you actually show, I've got something here which is very lean and mean, very difficult to kill with this kind of agent. And if you can show that to your cycle itself, then you also have the confidence that cycle actually works and does what you intended it wanted to do. So the VAPs most of the time say for decontamination of areas, and also again the loading patterns, but that applies to most of the chemical and gases. You must be sure that everything is accessible to this gas. And the nitrogen dioxide, it's just, I don't have too much experience with it, but it's got the same kind of thing. You're using a gas. Be sure that also when you got a loading pattern in there, that the accesses or surfaces that you want to sterilize or decontaminate are accessible for the product itself. Coming at the end already. This is a very high level kind of explanation that I gave at this moment. Every sterilization method itself can be complex, less complex, more complex. There are a lot of parameters, there are a lot of considerations, and when you're actually going to work with this kind of process, that I can give a course about every sterilization method for more hours to get into all the details. So the one thing I wanted to show you a little bit with this course is, okay, these are the most common sterilization methods in the field at this moment. Always try to go, if it's possible, say for a steam sterilization, because that is widely accepted within all the world. If you've got a good qualified process for that one, then you're most of the times you are okay when you show them the evidence. The other ones need a little bit more from your side. The mechanisms are well known. So for the gases, for the ATO, VAP, gamma radiation is also well known, but you have to do a little bit more effort from yourself, your studies, to show that that kind of method that you're using is fit for purpose, what you want to achieve with the materials and the loading patterns and the things that you want to achieve to get it sterilized in that way. So it's going to be a little bit more effort from your side. Also for the filtration part, you have to show it's not really that you say, okay, I put it over 0.22 filters. The material itself, the temperatures, flows, there are numerous kind of parameters you have to be aware of. So one of the things is, if you want to go into this sterilization part of your materials or media or something else, first look at, okay, can it be heat resistant? Can I use steam? Yes, no. If I got no, then I got other options. And when you got other options, just be familiar where the critical parameters are for these kind of processes. And there's a lot of information on the internet about it, these kind of things. Yeah, this more or less a little bit that I can explain at this moment and in this kind of detail. So hopefully it gives you a little bit more insight of the things that are now available on site.
Okay, Ronald. Thank you. Thank you very much for this great presentation about all the sterilization methods. And also thank you for all the tips and tricks you have given us. We all can use to properly implement the systems in our organizations. Thank you for that. So this concludes the training, the main part of the training today. We are really on time. We have 13 minutes for the Q&A session. This is very nice. So we're going to cover some of the questions we have already received today. So I would like now to open up for these questions, just to remind the audience that you can use the Zoom bar you have below your screen and click on the Q&A button. And there you can pose all your questions you have, right? So we have received some of them. So maybe let's start by, we have a question from Mainul. Mainul is asking, is it mandatory to check steam quality during the qualification of a steam head sterilizer?
Yeah, yes. Just like you want to have saturated steam during your process, because that you want to achieve to show that you then you have the best process that you can have. So it also starts also with the quality of your incoming steam. So you must also monitoring your incoming steam and the quality of your incoming steam, because yeah, that is the basis of your whole sterilization part. So yes, you have to check that.
Yeah, that's right. And another question related with that from Abdul is asking, during validation of the steam sterilization, how do we validate residue of a steam after the sterilization process?
Sorry, I missed the reducible.
Yeah, during validation, you're using a steam for sterilizing. Yep. And he's asking about how can we validate the residue of a steam on uniforms, for example, under sterilization.
Okay. Yeah, there are two. So the most commonly is just to work with a lot of temperature probes, say inside on the difficult places or the worst case places that you want to show that you have the temperature over there. Then you also come into a certain kind of topic that it's about materials that you want to steam sterilize. Sometimes we have very complex kind of materials. One of the most difficult things to sterilize are these endoscopes. Endoscopes are very long. They are very small openings just to getting into the steam. So one thing is, okay, if you have temperature probes on difficult places, and that you can rationalize, you can do an assessment on that, like pathways, thickness of materials, the heat, the transport of a material, if it's possible. Metal will do it better than glass. Then actually when you are going to a validation, then the last part before you actually go into sterilization, then you should have saturated steam on all your spots. So what you should see is that the temperatures go very quickly rapidly going up the same rate as your pressure is rising within your sterilizer. If one or two are lacking that, so you got to sort of phase down, it means that you don't have 100% steam on that spot. So, or it is too difficult, or your process is not good enough. But it should be very dynamic just before you're going into sterilization. And then you know you got saturated steam on that spot.
Okay.
Hopefully.
Yeah, I think it replies the question. If not, make us let us know. Related to the sterilization with the steam, there's a question from Joaquin. He's asking, is it possible to do a sterilization with steam, but using soft temperatures, like between 105 and 100, in order to skip the degradation of the final product?
That's a nice discussion. No, because if people have some experience with sterilization, they also should be known as a F0 value, which is sort of equivalent of the time that you would be sterilizing at 121 degrees. It's a theoretical calculation. And other people can say, okay, it's more or less because you want to have to know what the effect is if you are going a little bit higher or a little bit lower around the 121. So that's effective. I'm not in favor of lowering the temperature more than say what you say about the 10 degrees as you come into 110. Sure, theoretically it should work, but in practice it's a different story. So if you really want to use lower temperatures, you also mean that you will have longer kind of processes. Try then to back it up also with biological indicators on the spots to show, okay, I do it different than say the uniform standard of 15 minutes, 121 degrees. I'm doing a lower temperature, much longer time, but I'm showing with my biological indicators that it's still so effective as it would be at 121. That would be my advice.
Yeah, and what let's say tool or indicator would you use to check that the sterilization step has been done as expected? Joaquin is asking if he can use a bio-Borden indicator method, for example.
Yeah. So using say there are commercially there are a lot of bioindicators can be bought. So you can put them on the places where you with your temperature distribution show that those are the places that take the longest time just to get on temperature or difficult to be used. And if you put it there and you show afterwards that actually on that spot the bioindicator is killed, then at least you have something to show that the efficiency is still okay. Because I can go also I can say I can do it for 4 hours at 102 degrees. Theoretically, yes. Practice, I wouldn't dare it. But
all right, excellent. So there's an interesting question from Philip. Philip is asking about the electron beam sterilization. It is not mentioned in your training, but can you give us some highlights about that?
Sorry, that is very specialistic.
Specific.
Very specific. Sorry, I don't have any no experience into that one. So sorry.
Okay, great. Regarding the UV irradiation method, we have a question from Jonas. Are there any guidelines, official guidelines that he can follow for the UV irradiation methods?
For radiation, there are. Sorry, I don't know out of my head. For UV, just what I said, it's really not a sterilization. It's more of a sort of decontamination, disinfection where it's used. but for radiation, sure after this session I can look it up. But I know
never mind. As all these questions can be covered afterwards, so we will prepare the response, and you will receive it later on, right? All right. So okay, we have maybe some spare time for one or more questions. Okay, let's go to the Annex 1. So can you give us some highlights or a brief understanding about the sterilization concept that is covered by the Annex 1 of GMP? GMP?
That's a good question, because the current company, we're also looking into the update of the Annex 1 that has been done 1 or 2 years ago, but now it's becoming effective. Some other things are a little bit changed in wording, expectations. The Annex 1 is more based now on risk-based analysis and monitoring kind of plans. So what I can give as advice, what gave me a lot of help, is there's a website. It's from the European Federation of Pharmaceutical Industries and Associations. So if you Google, and I have to say it very quietly, then people can get their pen and write it down. It's EFPIA and Annex 1. If you Google those two words, you get a very nice spreadsheet of this association, which addresses every point from the Annex 1, also including sterilization, from, okay, this was the old, this is the new, and this is the justification, or how we say it. It gave me a lot of insight, because it talks more easily in wording than sometimes the pharmaceutical guidelines is. So for people who didn't have a pen, second chance, E is Edward, F, P, I, A, and the word Annex 1. If you Google those, then you come into this spreadsheet, which can be very helpful, not only for sterilization, also for other parts.
Right, very nice. Thank you for this reference. For sure, it's going to be very useful. There are lots of information about guidelines and so on, but a clear understanding of the Annex 1 is really important for sterilizing. All right, so okay, we have just 1 minute, so we are not over time, but I think it's time for the wrapping up. So because this is a 1 hour training, don't worry about all those questions that have not been covered today, right? We will make sure to reach out to you over with a PDF page after this training session. All right. So I appreciate everybody for being here to this training and for posting all your questions. I hope all your questions and responses from Ronald have been covered properly. And special thanks for Ronald today for being here today for this preparation of this training. This is a very long training. You have covered summarizing the key steps and the key issues about sterilization. Thank you very much also for being here and for covering that. Thank you to QBD. So thank you very much for all of you. And I think goodbye and have a nice training. Have a nice day. I want to say see you next training. All right. Bye-bye.
Bye-bye.